Okay, on we go to module 10 and 11. Modules 10 and 11 kind of blend into each other. It's all about molecular orbitals, module 10 is, and then 11 is about applying that to curved arrows. We've already kind of introduced curved arrows as a way to represent electron movement. With molecular orbitals, you really get a feel for what each curved arrow really implies. So first of all, just a general question. What are molecular orbitals? We abbreviate them as MO. So this is also called MO theory. So MO theory is basically another way to describe molecules that will give us insight into how they will react with each other. I want to give a disclaimer that the MO theory that we're going to use is very simplified. There are much more rigorous, more complicated approaches to MO theory that you'll be exposed to in future chemistry classes. What I want you to remember is those don't mean that what we're doing is wrong. Those just mean that what we're doing is a kind of zoomed out, simplified approach. In science, we use lots of different models, and usually you want to use the simplest model that gets the job done, that gets a particular job done. And if the job is thinking about how getting a basic understanding of how two organic molecules might react with each other, we're going to use the simplest possible MO theory. But it's by no means what you would call the most rigorous, most complicated form of ML theory. So that's just my disclaimer. We're going to use an oversimplified version. And there are going to be some things that I'm just going to say, memorize this. I can't give you an explanation. It's just a rule. Follow that rule. You can probably go on and learn explanations for those things later, but at this point, it's not worth going deeply into them. All right, so this is all going to go back to quantum mechanics. And so I want to quickly review what you should know about quantum mechanics. What you should know about quantum mechanics, again, is not to have some deep intuitive understanding of it, because almost no one has that. But you remember we talk about electrons being in orbitals. So you need to have a little idea of where orbitals come from. So where does an orbital come from? Where does an orbital come from? What's it based on? Any idea? What's the like underlying thing out of which an orbital is born? Yep. All right. An orbital describes electron density, and where does that description come from? What's beneath that description? A wave function. So each orbital is based on a wave function. We use the Greek letter psi to represent our wave functions. So a wave function is just a mathematical function, but in 3 dimensions instead of 1. So you're used to f of x. Psi is going to be a 3-dimensional function, so you can think of it as being a wave function of 3 variables, x, y, and z. More commonly, it's actually r, theta, and phi, but we're not going to do any of the math, so it doesn't really matter. So you can think of it as a wave function that you put in a point in space, and it spits out a value. All right? So you pick a point in space, and you put it into the wave function. Psi is the wave function. The input is any point in space around the nucleus, and the output is you get some number that has actually no physical meaning. So then you're really annoyed because you're like, all right, well, why would I bother inputting something into the function and then getting out some number that has no physical meaning? Well, it turns out when you square that wave function value, or in reality it's even more complicated because psi is a complex function and it has a real part and an imaginary part, so you're not actually just squaring it, you're multiplying by what's called its complex conjugate. But you don't need to know any of that. What you do is you then square the value, and you get psi squared at that point in space, and that actually represents the electron density. Now, we think of orbitals not as mathematical functions, we think of them as pictures, right? So the question is, how do I get from this to those pictures of orbitals that we've seen? We're essentially graphing it. We're picking all the points in space around the nucleus. We're finding the psi squared value, and then we make a picture that shows where the electron density is high, and we call that our picture of the orbital. So when we actually map all the points in space the space around the nucleus, what we get is a picture that represents where electron density is high. And those pictures, you know, we're used to an s orbital looking like a sphere, and p orbitals looking like this, or like this. D orbitals, which we don't really deal with in organic chemistry, look like that. All right. So there's this process. We don't have to do any of this process in this class because someone else has done this whole process for us. All right. The only reason I bring this process up is because when we want to create new combinations of orbitals, when we want to create molecular orbitals, we need to take it a step back to the wave function value step before we square the wave function value. All right. So one thing to note is that the wave function value itself, this may be positive or negative. When you then square it, what is always true about psi squared? It's always positive. So whether the wave function is positive or negative actually has no impact on the electron density, right? Negative 2 squared and 2 squared give the same electron density value. But there is some residue, there is some, the wave function value is going to be important when we start combining orbitals. Because when we combine orbitals, what we do is actually add the two wave function values. So, 3 plus negative 2 is a lot different from 3 plus 2. So the pictures that we draw of orbitals do have this indication in them of whether the wave function was positive or negative. What is the indication when I make the pictures? I haven't included it in these pictures yet. But they'll have shading to indicate whether the wave function value is positive or negative. For an s orbital, it doesn't really matter because the wave function value is going to be the same throughout the sphere. But for p orbitals, generally one lobe is shaded and one lobe is unshaded. In d orbitals, they'll have 2 shaded and 2 unshaded. That shading doesn't indicate any difference in electron density. The electron density is the same in the shaded and the unshaded part. What it represents is just this reminder that the wave function has a different sign on those two sides. And that difference in wave function sign becomes important when we start combining orbitals. Okay, so here, shading just represents different wave function sign. Doesn't really matter which we call positive or which we call negative, like whether shaded is positive and unshaded is negative, or vice versa. The important thing is that the two lobes of a p orbital are opposite. All right, so I bring this up because we're going to be combining orbitals together, and when we combine orbitals together, we need to go back to the wave function value step. So the before it was squared part. In order to make new orbitals. So MO theory is going to be based on combining the two orbitals on two different atoms to create new orbitals that are shared between the two atoms. So going back to this idea of what is MO theory, we say in order for a bond to be formed, two atoms share electrons. That also means they're going to share orbitals. So really this description will involve sharing orbitals among atoms. Makes sense. We say covalent bonding is sharing electrons. In order to do that, they've got to share orbitals. So what I'm going to do in my discussion, I'm going to repeat a lot of the points that come up in the reading. I still encourage you to do that reading. I think the reading is a really good description. I just think it's nice to hear these complicated ideas in a couple of different ways. So, you know, this is to go in conjunction with the reading. You might find I'm repeating a lot of what you've already read. That's okay if you feel like, I got it all from the reading. You don't have to watch all of this. But if you feel like, all right, I could use a little more description, then this will be a good resource. All right, so we said back in Module 5 that in order to make bonds, two atoms have to have their orbitals overlap. And when their orbitals overlap, what we can do is combine those two orbitals by adding their wave functions together. And when we combine their wave functions, that's what's going to result in molecular orbitals. Turns out that there are two different ways you could combine them. So one possibility is when you combine the two orbitals, they overlap and they have the same sign. They're both positive or they're both negative. We call that in-phase overlap. Out of phase overlap would be one of them is positive and one of them is negative. In this language, in phase and out of phase actually comes from, the physics of waves. If you've ever been in a pool where you took like a boogie board or something and started making waves in the pool, you know that those waves start bouncing off the wall of the pool and they'll come back toward you, and you can, by timing your motion, either make the new waves you're making cancel out the other ones by timing them so that one is up when the other is down. That would be out of phase overlap. Or you can make the waves get bigger by timing things just right. So when the wave bounces off the wall and comes back, you're now adding to it and instead of subtracting. That would be in-phase overlap. How many people have ever used noise-canceling headphones? Oh, wow. Not a lot. I thought they were more popular than that. Well, so they're built on the idea that sound travels in waves. And so when sound comes in from the outside, if you create a wave that is out of phase with the incoming wave, you can basically cancel it out. That's what noise canceling headphones do. So we use the language of what we call constructive interference and destructive interference to describe in-phase and out-of-phase overlap. These terms are not necessarily, I'm not going to test you on the terms. It's not necessarily that important that you memorize the terms, but you may hear them from time to time. So constructive interference is the idea that when you have two wave functions with the same sign and you add them together, here I have a graph of what I'm calling psi 1 and a graph of psi 2. What am I going to get if I add together psi 1 and psi 2? What would my graph of psi 1 plus psi 2 look like? Over here on the left side. Psi 2 is really, really small, right? So my graph of psi 1 plus psi 2 over on the left side should look very similar to just the graph of psi 1. So it's going to start out like the graph of psi 1, but then as psi 2 gets bigger, it's going to start to go above the graph of psi 1. And same thing on the left side. Well, so the question is, why did I dip down in the middle? I don't know. I guess it's a question of how tall this gets from here. I kind of tried to double that. So it should go up to about there. I don't know. So there may still be a dip down in the middle because there was a dip for those two in the middle. But the exact drawing doesn't matter. The important thing is that when we add the two wave functions together, what's true of the wave function value for the combined wave function? It's bigger. We call that constructive interference because they have built on each other. So in general, when two wave functions, what we say, constructively interfere, the magnitude of the wave function increases wherever they're overlapping. If the magnitude of psi increases, what happens to the value of psi squared? It increases. And so, if the value of psi squared increases, are we more or less likely to find the electrons in that area? We're more likely, because psi squared represents the electron density. Alright, this slide is the key. If you didn't take down the graphs, that doesn't really matter. I should have said that before I even started that slide. So actually, I'm going to go back to that for a second. Don't copy this slide. All right, so what this means is the shape of the orbital will change, right? We want to deal with the pictures. We don't want to deal with the mathematical stuff. We want to deal with the pictures. So if I'm making it more likely that the electron shows up in the overlap area, the way that's going to affect the shape is that it will get bigger in the overlap area. The orbital gets bigger because the orbital just represents where is the probability high. It'll get bigger in the overlap area and it'll get smaller elsewhere. Okay, destructive interference, as you might imagine, is just the opposite. Again, don't copy down this slide, but the result is important. So if instead my two wave functions look like this, one of them is positive and one of them is negative, now when I combine them, what's going to happen in this area where they overlap? Well, I'd start out on the left, it's going to look a lot just like psi 1, but then psi 2 is going to start subtracting from psi 1. And so this is going to end up below psi 1, and then at some point right in the middle, they completely cancel each other out. This point in the middle where the wave function goes to 0, we call this a node. A node basically represents a spot where you don't find the electron at all. So that means the electron density there around that area is really small. Everyone likes a little graphic there. The two individual wave functions falling away. All right, so for destructive interference, when wave functions destructively interfere, what happened to the magnitude of psi? It decreases. And when the magnitude of psi decreases, what happens to the value of psi squared? It also decreases. And a smaller value of psi squared means you're less likely to find the electrons in the region of overlap. So wherever the orbitals are overlapping now, we're less likely to find electrons there. And another result of that is, well, if we're less likely to find them in between, that means we must be more likely to find them elsewhere. So the shape of the orbital changes. It gets smaller wherever the two atomic orbitals overlapped, and it gets bigger wherever they didn't overlap. If nothing else, if you can take away this, how to use the pictures, combine the pictures, and make the new picture of the new orbitals, you'll be in great shape. All right? All that other stuff is just background, so you have some idea of where it came from. But what we're going to do is just make new pictures based on this idea, that we can have in-phase or out-of-phase overlap. What questions do you have? In phase goes with constructive, out of phase goes with destructive. All right. So the simplest example I can give you comes from the molecule H2, because hydrogen just has what orbital? An s orbital. So H2 would involve an s orbital on one atom, and an s orbital on the other atom. So imagine I take two hydrogen 1s orbitals. I'll do one in, actually, why don't I do them in different colors? Do one of them in red, one of them in blue. All right. So here, if they have the same phase, both of these are unshaded. This is going to be constructive interference. When I combine them in this way, I'm going to make a new orbital. What kind of bond would we say two hydrogen atoms make? A sigma bond. So I'm going to call the new orbital sigma bonding orbital. And what is my sigma bonding orbital going to look like? Well, in the area where they're overlapping, it should get bigger. So my sigma bonding orbital is going to look kind of like this, where it's, and if I put in the two nuclei, what we would find is now there's more electron. Yeah, you could totally draw a little person in there. What we find is there's more electron density between the two nuclei. All right. Why would we call that a bonding orbital? When I have plus, plus, and minus, what does the negative charge tend to do? It pulls the two nuclei towards the middle, right? This pulls the nuclei because that's the electron density. Remember that the orbital represents the electron density. So the name bonding, we call this bonding because it's pulling the nuclei together. And if we think about potential energy, electrons are going to be lowest potential energy when they're as close to a nucleus as possible. Well, if you were an electron, would you rather be close to both nuclei or close to one and not close to the other? You'd rather be close to both. So it turns out this bonding orbital has lower potential energy than the individual atomic orbitals. So it turns out that, that's another way to describe the bond between two hydrogen atoms. Now, to go along with this, there's a rule in quantum mechanics that says orbitals have to be conserved. Basically, you can't take two orbitals and combine them and make just one new orbital. So we have this rule that says if we're going to combine two atomic orbitals, we need to make two new orbitals. So one of the new orbitals we make is a sigma bonding orbital. Turns out we can also combine them and make what we call an anti-bonding orbital. And every time we create a bonding orbital, we're going to create a corresponding anti-bonding orbital. All right? The thing that's going to be different is, in this case, I'm going to take a hydrogen 1s and I'm going to essentially subtract the other hydrogen 1s. I'm going to combine them out of phase. So I might have my red one like this and my blue one like this, but one of them is shaded and the other one's not. What happens when I combine two orbitals out of phase? Destructive interference. So what will happen to the electron density between the two nuclei? It'll decrease. That'll mean it'll increase everywhere else. We're going to call this a sigma star antibonding orbital. And in this orbital, now if I have nucleus 1 here and nucleus 2 here, now the bulk of the electron density is going to be on the outside. All right, so the question is, are they pointed in? The actual shape doesn't matter that much. You know, the reading has better representations of the shapes. We get what we call a node in the middle, where there will be no electrons. All right, and I'll have to continue with that tomorrow, but I wanted to at least introduce this idea that every time we create a bonding orbital, we'll create an antibonding orbital.